Hello everyone, welcome to Gate Academy Global. In today's short span of video, we are going to understand one of the amusing fact regarding the transmission line. As far as this topic is being concerned, the electrical guys study this topic within power system analysis and electronics people study this topic within the EMFT. As far as the core structure of the transmission line is being concerned, the transmission line has been a parallel conducting structure which connects source to load. Like if I take an electrical side, towards one side you will be having source. Like I had been making this video from Korba, and the Korba has been power hub, so you can say one of the power plant is going to generate the power, and that had become a source to this transmission line. And towards another side we are going to have load. We can have any of the plant, like we can have a steel plant, and where the power is being supplied from the Korba, and this parallel conducting wires would be called as a transmission line. Similarly, if I take an example from the electronic side, you must have seen this coaxial cable, which you also call a type of transmission line. Towards rooftop, we used to have a dish antenna. Dish antenna is being connected to this cable, and this cable is being terminated towards our setup box. Again, it's been a type of transmission line. I would like to ask one important thing. If the transmission line has been a conducting structure which connects source to load, then why we studied this topic separately within PSA as well as electromagnetic field theory? Because within the network analysis, already we had come across many of the situation where we had the source, the conducting structure was connecting to load. My dear friend, the different theorems and different laws which we had studied earlier, KVL, KCL, Thevenin, Norton, Telgun, they are no more applicable over the transmission line analysis. The analysis has been completely different. Now, the things should be coming in our mind, sir, why the analysis has been completely different and why within the network I could not study the transmission line analysis. For that, what you had to do, you had to go into this study. What I had done, I had taken a source. Now the source has been connected to a conducting wire, and towards right hand side I have connected with the load. So far my basic assumption in network was the signal was traveling over the conducting wire with the infinite speed, and as it had been connected to a conductor and the signal had been moving with the infinite speed, so signal time would be taken from one side to another side is simply being zero. So the moment the source is getting connected, the same voltage is being experienced by load. But practically it had been seen the signal is not traveling with the infinite speed, it travels with a certain finite speed. And as it travels with a finite speed, now the problem do come into the picture. See, what are they? See, I have presumed the length of this two parallel conducting structure, which I am calling a transmission line, is being L. And let's take the signal is being moving on this transmission line with the speed of V. So may I know what would be the time taken by the signal to reach from one side to another side? Obviously, from time, distance, and speed formula, we could have taken that time is been L divided by of Vp. And may I know what had been T of R over there? The T of R is been transient time, the time taken by the signal to reach from either of the side, from this side to this side or this side to this side. Okay, sir. But anyways, why we have been calculating this? This has been a very, very critical variable. See what happens. I had taken a time varying signal. For the time being, I had taken a sinusoidal signal. Sinusoidal signal has been a type of periodic signal, so obviously we are going to have its period as well. The time taken by the signal to start repeating itself. Let's take its been capital T. Now what we had been doing, we had been comparing the transient time and the time period of the signal. See what had been happening. If time period of the signal has been much higher than the transient time, the time taken by the signal to reach from one side to another side, what would happen? That means this signal has been so sluggish. As the signal has been moving from one side to another side, the voltage towards the input side has not changed much. Or I would say the complete transmission line has been equipotential line. Equipotential line. At any moment of time, whatever the voltage do you have over here, the same voltage has been there also. Put together, the lump network analysis can be easily used, where we can apply a KVL and easily we can find the current I. Fine, sir. Fine. So here I can use the lump network analysis. But the problem do arise when the capital T is being very smaller than TR. In that case, what happens? Do you know that? The signal, let's take, this has been a 50 sine omega t. 50 volt is being transmitted at any moment of time. Let's take omega t is equals to 0 radian. 50 volt is being transmitted, and as the 50 volt is been moving towards load side, what happens? The input has changed its worth. and now the new voltage would also follow towards load. And end of the day, what had been happening, there are so many voltage had been transmitted and has not been received by load yet. Put together, this complete transmission line is no more equipotential line. Sometime you will see here the voltage at same time, here it has been 50, here it has been 40, here has been 48. And once you'll talk about the direction of current, you can see higher potential to lower potential, higher potential to lower potential. Can you say you had a uniform loop current? No, you did not have uniform loop current. And even this conductor had the different potentials over its length, Now, can you tell me the KVL, KCL, should I be applied? No. So may I know where the actual problem was lying? The actual problem was lying if T is being much smaller than TR. Actually, the electrical people are been facing the problem from length side, and electronics people are been facing the problem from frequency side. See, in electrical engineering, you can say your power plant would be kept somewhere here, and your load might be kept somewhere maybe 1,000 kilometers, 1,500 kilometers. Like your power plant has been sitting in Chhattisgarh, and let's take the load has been sitting at Rajasthan. So what had happening? See, L is been quite larger in case of electrical engineering. If L divided by VP, L is been quite larger, what would happen? Obviously, TR is been quite large. And once you'll compare with T, what used to be the T in electrical engineering? If you take single phase power supply, the F is gonna be 50 hertz. So 1 upon 50 is gonna be 0.02. So what I'm saying, 0.02 has been much larger than this value. So obviously, electrical people has to take care of the complete transmission with the help of transmission line analysis. They can't use the KVL, KCL, lump sum value or lump sum analysis. They can't use that. Electronics people, actually they are not worrying about length. Like dish antenna has been connected with the coaxial cable, has brought towards your digital box. How much length it would be? Merely 40 meters, maximum 50 meters. So length has not been a big concern. My big concern has been the frequency. As the frequency is very larger, T would be much smaller. In communication, obviously, frequency would go in megahertz in video signals. So what would happen? Now the T has been much lesser, and still this condition is being satisfied. So what is been the conclusion? This complete length is not going to be equipotential because of length for electrical signal or electrical side, and similarly because of frequency in electronic side. So both of them has to study something else, because they can't use the KVL and KCL straight away. They had to invent something new, and that had been the analysis of transmission line. In transmission line, what we do, the complete transmission line is being bifurcated into the infinitely small segment. Why did I do so? Because if the length is been infinitely small, the T of R is almost zero. If T of R is been almost zero, you can use the lump network analysis. So what we are going to do, we are going to analyze the lump network analysis. Here the KVL, KCL, everything would be valid, because within a short span of time there would not be any effect of transit time. And yes, we can use the lump sum analysis. Now this lump sum analysis has been extracted from source to load, and the complete transmission line has been made. And that is why you must have seen the effective series resistance, effective series inductance, effective parallel conductance, effective parallel capacitance is being calculated per unit length. And you must have seen in case of transmission line analysis, the distributive elements are being calculated in per unit length. Did you have understanding why the transmission line analysis has been quite different than the network analysis, although the source is being connected to the load? Because of length, because of frequency. Length had the problem for the electrical people, and frequency had the problem for the electronics people. Is that part clear? Bye bye, take care.